Hey everybody, I hope you're doing well today. Today in chemistry, we're just going to continue on. And like I said yesterday, we're going to talk about the atomic mass. And so the atomic mass is this other number that we see on here. And so um, I know sometimes if you were looking at like carbon and it had 6 protons, 6 neutrons, and you get carbon 12, that's really close to this mass number. Um, but that's not actually what that is. This is the atomic mass. And so again, we're going to work towards finding that today. And so before we can get there, we have to talk about some ways in which we mass atoms. Um, I guess not necessarily the way, but the units that we use to do so. And so I'm going to switch it over to my computer instead of my iPad and find my screen. And so how we measure atoms is we use the AMU as our unit, so the atomic mass unit. The reason we use AMUs is because grams are not good for measuring numbers of atoms or the mass of atoms. Atoms are so itsy bitsy teeny weeny that grams just doesn't really match up. In fact, an AMU is about 1.67 times 10 to the negative 24th grams, which is this many grams. And so the AMU is really small, and so it's really good for measuring uh, things like atoms. And so just in terms of our subatomic particles, what are the mass of those? Well, over time, scientists have been able to identify those masses. And so the mass of a proton is approximately 1 AMU. The mass of a neutron is also 1 AMU. And electrons are a very small fraction of the mass of a proton. And so their mass is really, 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 really small. They do have a mass, but again, it's so small that it doesn't really affect the overall mass of the atom, at least in a way that affects any calculations that we may do with them. And so the mass of the electron is often considered Z0 AMUs. Again, it's not truly massless. It's just so small that we consider it negligible, and so we say it's massless. So we treat it as being a massless particle, but there is no such thing. So if you wanted to calculate the mass of an atom, well, it would pretty much be the same as the mass number, because if we have protons with a mass of 1 AMU and neutrons with a mass of 1 AMU and electrons with a mass of 0, well, then all your mass is just coming from your protons and your neutrons. And so the mass of an atom would be the same as the mass numbers. And so, for example, here we're looking at carbon 12. Carbon 12 has 6 protons and 6 neutrons. Each one of those has a mass of 1 AMU. So if you have 12 total particles and they all have a mass of 1, the mass would be 12 AMUs. However, in nature, we don't really see this happening, or I guess that's not the mass that we report on the periodic table. And so why is that? And so in nature, most elements don't exist as one type of atom. They exist as multiple isotopes of that element. And so they have different numbers of neutrons. And so again, in nature, most elements occur as a mixture of 2 or more isotopes. Each isotope of an element has a fixed mass and a natural percent abundance. And so over time, we've studied the isotopes of elements and saw how often we found those in nature. And so we know the percent abundance of those. And so the mass of the elements on the periodic table is an average of all of those isotopes that we see. And when we calculate atomic mass, it's actually going to be a weighted average, because it doesn't just depend on what isotopes are present, it also depends on how often we find those. And so uh, we'll look at that some more. But our atomic mass, again, is just the weighted average mass of the atoms in a naturally occurring sample of the element. And so weighted average, again, it takes into account the mass of your isotope and also how often you find that isotope. And so if we were looking at copper, the atomic mass of copper is 63.546 AMUs. we want to know which of copper's two isotopes. So in nature, we can find copper in two forms. We can find it as copper 63 and copper 65. The atomic mass, and we want to know, I guess, which one of these is more abundant. And so since the atomic mass is closest to 63, we know there has to be more 63s, copper 63 than copper 65s. And so you could just think of that as if I had one atom of copper 63 and one atom of copper 65, then the average would be 64. Well, if I had another 63, the average would drop below 64. And if I had another 63, it would drop even lower. And so our average gets closer and closer to 63. So the more copper 63s we have, the closer our average gets to 63. And so that's why this is skewed closer to 63 than 65, just because there's more copper 63. And so just going back here and looking at our isotopes, again, these are studied in nature. And so again, we know how often we usually find these. And so copper, or we're looking at hydrogen right now. Hydrogen with one proton and no neutrons, which is hydrogen 1, occurs in nature 99.9885% of the time. And so the most hydrogen atoms only have one proton. If I add a neutron to it and I make hydrogen 2, I do see that this does occur in nature. It occurs 0.0115% of the time. And so those are the two main isotopes of hydrogen I'm going to find. Again, if I add another neutron here, it becomes very unstable. We can still find it in nature, just very, 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 very small amount of it. And so usually things that are unstable are going to decay over time. And so that's when we have elements that are radioactive. They break down over time, like carbon 14 will break down into carbon 12 and carbon 13 over time. That's why we can use it for carbon 14 dating, is because we know how quickly it decays or how fast it breaks down into those other forms of carbon. And so we can figure out how long something's been dead, for example. If I added another neutron, I would make hydrogen 4. And notice that that does not occur in nature. It's way too unstable to occur, and so we do not see it. We can look at some other ones, so like oxygen. Oxygen 16, so 8 of each, 8 protons, 8 neutrons, occurs 99.757% of the time. If I make it oxygen 17, 0.038% of the time. If I make it carbon 18, 0.205% of the time. And so this one actually has a higher abundance of oxygen 18 than oxygen 17. And we can see that in several elements. It's just what's most stable and how they're most likely to form. But then you see that there is no carbon 19. And so that's just looking at the abundance of them. Again, we can study this in materials, and we can break it down and figure out how many atoms of each isotope we have. And again, that's how we find that percent abundance. And we've used that to calculate the atomic mass of all our elements, which is what we use on our periodic table. I'm going to make another video here for calculating atomic mass because this one's going to run too long and YouTube won't let me upload it. So I'm going to stop this one here and then start a new one.